Hello everyone, welcome to the third lecture of week 10. So we've been discussing about parameter efficient methods. We talked about LoRa and its variants. Now we will do what else we can do with parameter efficiency to improve that, and why is that needed, right? And we will talk about quantization and specifically focusing on QLoRa, and that will take us this lecture and the next one. So that is the title for the lecture: efficient fine tuning for quantized language models. So to talk about this, to give motivation that why do we need to go beyond LoRa, we will briefly talk about the memory requirements for GPU, okay, and then we will say, when we go for full fine tuning to LoRa and QLoRa, how much is the change in the memory, right? That is the requirement for these methods, that not everyone has GPUs that can fit large models, that can fine tune large models. So how do I ensure that large models can also be fine tuned with, say, much smaller GPUs? Now for talking about QLoRa, we will discuss the concept of quantization, and we will discuss the ingredients required for QLoRa. We will talk about one ingredient in this lecture, normal float 4, and the other few ingredients in the next lecture. So let's talk about the memory requirements for GPU. Say suppose you are training or fine tuning a language model which has theta parameters. So theta is the number of parameters, right? And we are talking about a particular setting called mixed precision setting. So you will see somewhere we are talking about 32 bits, and somewhere we are talking about FP32 and FP16. They are two different settings. So you need 32 bits, so you need 4 bytes here, and FP16 you need only 2 bytes. Right. So it's a mixed precision setting. I'll talk briefly about the setting in the next slide. So under this setting, what happens? So your gradient and model parameters are stored as FP16. So you need 2 bytes per parameter. That each parameter will have the parameter value and the gradient with that. So you have 2 theta each, right? Where else do you need the memory? Now see, we talked about Adam being one of the very interesting method, but it's very bad in terms for memory. Because for Adam, I need to store the momentum and also the variance, right? So we remember that momentum and variance, and I need to store that for each parameter, right? Across previous iterations, how much is the momentum and variance, the squared momentum, and I also need to store the full FP32 state of all the internal parameters. So that means I have 2 copies of parameters in FP32 and also in FP16, and this I'll say briefly why this is needed. But with that means you have 4 plus 4 plus 4, 12 bytes per parameter needed here, 2 bytes needed here, 2 bytes needed here. You need 16 bytes per parameter. So that means if your model has theta parameters, you have 16 theta, right? That much memory that you need. So something like a 7 billion model, like Llama 2 7 billion model, you need 16 cross 7, right? 112 GB of memory, right? That's huge, right? So you may think 7 billion parameters, how much memory would I need? At least 112 GB. This is without optimization. There are certain optimizers that can reduce it, but give some idea. Okay, like I talked about mixed precision setting. What happens there? So you see, we are working with F16 and F32, 2 bytes and 4 bytes. And typically what you do, all your computations typically you do with FP16, right? But when you finally want to update your weights, you update in your master copy of 32 FP32. Why do you do that? Because it has a low precision, right? It doesn't have a, if you increase the number of bytes, you will have better and better precision for representing a particular number. We'll talk briefly about that. So if you increase the number of bytes, you will get a better precision. Why that is needed? Because otherwise what is seen, So the weight gradients, when you multiply by the learning rates that are also very small, this may come out to be very small, and it has seen say 5 to 10% of the entire updates will come to 0 in FP16 format. So that's why you have to make use of. So when you do the final update, you do it in the model, the master weights, right? So that you do not lose those updates. But then you again convert it to F16 and work with that, right? So this is the mixed precision setting. So that means this you are storing 2 copies of that, one in of parameter weights, one in 32 bits, another in 16 bits, right? And that is the mixed precision setting. And this is shown to be working better than either using just a single precision setting like FP16, because then you will not be able to save those 5-10% of parameter updates, or if you do full 32, you will need even more. I mean, this will be even more inefficient. What else is needed? So we talked about parameter updates and all, but there are also activations. Remember, I mean, in deep neural networks, you have activations and the weights separately. So this memory we talked about is the parameter gradient and all that. But you also have to have activations stored. Now, how much memory do you need? Now, this is one analysis from this paper, right? So you see, let's say you are when you are actually working with this, you have a sequence length, right? So let's say you have S number of tokens. So S is your sequence length, and you have a batch size. So you will take some B sequences. Now it is using H as the model dimension. We used D model, but let's say H is my model dimension, D model, and you have A as the number of attention heads. In terms of these, what is the activation memory? So you see where do you need it? So first of all, you have S is the sequence length, B is the batch size. So for each of the token, you need the embedding dimension, that is H, that is D model, right? So S, B, H, and these values, all of these will be in 2 bytes, right? So we are working with 2 bytes for each value. So you need 2 times SBH as the input, right? So for all query key and value matrices, you will have 2 SBH as the input, a common input for all of these, that much memory. Now when you multiply Q K transpose, you have to get the Q and K matrices, right? So again, each of that will be of the same dimension. So you will have because you see, you talk about number of attention heads times. So as such, for each matrix it may be small, but you think about the number of attention heads, so it comes back to the same dimension as H. So you will have 2 SPH for query, 2 SPH for key, right? And then you will have the softmax output. What will be the dimension for that? So you will have, if S is your sequence length, you will have S cross S matrix for all QK transpose, S cross S, and you will need it for all attention heads. So S cross S times A, and you will need it for all batch, and this is 2 bytes, so this much. And there are some more things for dropout that I am not going into detail, right? So same for values. Values also you will have 2 SBH, right, as the input, getting the values. And so if you add all these, you get 11 SBH plus 5 A S square B storage. What else is remaining? Now the feed forward network. So feed forward has again, so there are 2 layers. One has SBH, another has 4 SBH. So we need SBH and 4 SBH, and do 2 times the number of bytes. So 2 SBH and 8 SBH. And because you use Galois nonlinearity, you again need 8 SPH for backpropagation. There is some dropout, so there are 19 SPH here. Layer normalization, you do it twice, so SPH into 2 bytes. So you have 4 SPH for layer norm. So if you add all these, this is what you get, SPH times 34 plus 5 times AS by H. This is per layer, right? Now you multiply it with the number of layers L. That much memory, right, you need. So just take a simple scenario like you're doing llama to 7 billion with a sequence of 256, batch size of 8, and your model dimension is 4096. You have 32 layers and you have 32 attention heads. So if you do the calculation, you will get it to be roughly, so you see 8 times 32 times 256 divided by h, right, 8 times s by h. So 256 into 4 will be 1024. So it will be 8192 divided by this. So this will come out to be 2. So 5 times 2 10 plus 34 44. So 44 times b is 8 and s is 256. So 256 cross 8 is roughly, right, so 2 into 1k, right, and h is 4k into 44 into 32. And you see this is also roughly 1k, even more. So more than 1k. So you get 1k 3 times. So you already have a GB, 4 times 2. So roughly like 8 GB or more memory for this particular configuration. It depends on sequence length, batch size. For activation memory, right? So we talked about the model state memory. You also need activation memory, and they add up. So that much memory is what you need for training your models, fine-tuning your models. So now this is from the slides of the Kilora paper. They did a little bit more conservative estimate, where they said, okay, let's use SGD with momentum. You don't need to store variance. So they found that for weights you need 16 bits. So same as ours, gradient 16 bits. Optimized state they were doing 64 bits. We were doing more. So even then you need 12 bytes per parameter, right? So if you have 70 billion model, you need 840 GB of GPU memory, right? I mean, so this is like 36 times some normal consumer GPUs that are at like 24 GB each. So you need like huge setup for just for fine tuning a Llama 70 billion model. Right. Now what happens if I use LoRa? See, when I use LoRa in fine tuning, see, this will not change. You still will have the same weights. What will change are these, and that they showed that you can have 16 bits. You still have 16 bits for that. This will be reduced by a lot, 0.4 bits, 0.4 bits, 0.8 bits. So total you have 17.6 bits per parameter, roughly, let's say 2.2 bytes per parameter, right? So then you can for 70 billion model you can store in 154 GB of GPU memory. It's still like 8 consumer GPUs, right? It's still large. Who would, not everyone will have 8 GPUs of 24 GB each. So that's where the idea came, that can we do even better than that. So the way you can do better is you have to save here, right? Can you do better than 16 bits? Can you reduce here? And that's where the idea of quantization comes in. So in QLoRa, so you just use 4-bit, right? So you just use 4 bits to represent this. So your weights are 4 bits and everything else remains roughly same for the LoRa part. So then you get roughly, I should be 5.6 here, but yeah, let's say 5.2 bits per parameter. So you multiply by that. So this is for 70 billion model. Now you need, this is less than 1 byte, right, per parameter. So you are saving a lot. You can do it with 46 GB of GPU memory with just 2 consumer GPUs. So you see there is a huge saving. Starting from 780 GB, we are going to 46 GB by doing LoRa and QLoRa, right? So this is the full fine tuning, LoRa and QLoRa, and they had various tricks for achieving this. So this is again some examples like T5 11 billion model. You may need at least 132 GB for full fine tuning, but with QLoRa you can do it with just 6 GB, right? Much more reasonable. Mistral 7B 84 to 5, Llama 270B 840 to 46 GB, right? So you see the amount of memory that you are saving. Now how do we do that, right? I mean, given this motivation, how do we achieve that? Now when we talk about quantization, we can even do quantization for the trained models. So let's say you have trained a model and I can do quantization after that. So this is called post-training quantization. So you take the weights of a model and quantize them to a lower precision, and we will see examples on how do we actually do this. But what happens, because they were not trained with low precision, it degrades model performance, right? So you really have to deal with that. I mean, you will not have the same performance. While what we are talking about is quantization aware training. So we are doing quantization during training time. So it is aware and is trained with that quantization, right? So you the weight conversion process is integrated during the training process, and this gives you a good model performance. You don't lose your model performance. So this is QLoRa is an example of quantization aware training. So what we will do here, so we use a very high precision technique to quantize a pre-trained model to 4-bit. That is one of the main things. Rather than going 16 bits, we want to go to 4 bits, and then you do LoRa adapters, and you will have backpropagated gradients through the quantized weights. Okay. So now what is quantization? Let's get some idea of what is quantization. See, in general, think about a number between 0 to 100, right? Now this can be any real number. Now if I ask how many bytes do you need to represent that fully, I mean, you cannot, if I'm giving you a finite number of bytes, you cannot represent that fully, right? You will always have some precision error. So you need infinite bytes to represent it fully. But let's say I say, okay, let's say I want to get the integers correct, right? So I just want the whole numbers. So take a number, you find the nearest integer, like that you represent it. Then I have only 100 possible representations, right? So how many bytes I need for 100 possible representations? So I can do it with 2 to the power 7, that is 128, right? So 7 bits will be sufficient. So right, 0.875 bytes are sufficient to represent any number between 0 and 100 if I am ready to give up on precision, right? So I'm okay with just the whole numbers. What if I want to, I'm even okay with giving up more. Say I'm okay if you tell me if it is between 0 to 10, 10 to 20, 20 to 30, right? I don't need the exact value. Then you have just 10 bins in this 0 to 100, right? And how many, you can just do it with 4, right? I mean, 3 bits will give you 8. So I think with little bit more than 3 bits. So you get the idea, right? You get roughly 0.5 bytes would be sufficient. So rather than using say 4 bytes to do a very good precision, you can go to 0.87 bytes and 0.5 bytes. If you are okay, if you can give up on the precision a bit. Right now I will not know whether this number was 27. I will know only that it is between here to here. Right? I can call it 20, for example. Okay. Now let's take a real example of converting from say 32 FP32 to 8-bit integer. So FP32 will have some numbers, right? 32-bit floating point numbers. So let's say these are some real numbers: 1.5, 2.3, up to 10.2. I want to convert these to int8 format. So how do I quantize these? So what I can say, okay, what I will do. So this is what is given in the QLoRa paper also. So see, int8 ranges from, so int8 means 8 bits, so you can do 255 things. So you want to take care of negative positives, so you can do from -127 to 127, right? And you of course have 0, so you have 127 plus 127 plus 0, 255 numbers, right, with 8 bits. So the maximum is 127, right, at the abs max, absolute max. So you see, okay, you find the absolute max in your actual numbers. So here the absolute max was 10.2. So 10.2 you will scale it to 127, right? So you will say, okay, so that's why you have 127 divided by abs max, the maximum of that. So 127 by 10.2, and then the actual number. Say the number was 10.2, so it will go to 127. You will use 127 to represent 10.2, and if the number was 1.5, you will use 127 divided by 10.2 into 1.5. So this becomes a constant, right, for you, and you multiply each number by this constant, right? And then because you want to get a number between -127 to 127, only whole number, right, you have to round this, get it to the nearest integer, yeah, and this will tell me where exactly this will come. And then wherever it comes, I have these numbers, I can use 8 bits to represent that, right? So from 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1, 1, 1, for example. I can use these bits, right? But there can be other ways of doing that. So just an idea. So this is my constant, right, for this. So this is why if FP32 constant C, and I use this C to multiply to any number, right, and I can quantize this. So like this example, this was my 127 divided by 10.2. Now I can multiply, this is my constant, I multiply each number by that, okay, and I get the corresponding int 8 numbers. You see, they will be between minus 127 to plus 127. In this case, they were all positive, so you have positive, but you could have got negative numbers also. Okay, and see, this abs-max can be a negative number. See, for example, here this was minus 10.2. It will not matter. I mean, you will still say abs-max, absolute max of this. Okay. So this will go to minus 127 in that case, right? This will go to minus 127, but the constant will remain the same for you. Okay. So that means I can quantize FP32 to int 8 using this particular formula, where we understood how to find this constant, right? So I have this constant multiplied with all the numbers. Okay. Now I will have to, so this is a quantization process, right? But I will have to dequantize them back to be able to use these. So this is one important thing. You quantize to save it in less memory, but when you actually have to work with these, you have to dequantize these, right? So you have to get back the original number. So how do you dequantize this? Okay, you can say, okay, I have a number, int 8 number, I divide it by this constant, and this will give me an approximate value of its 32 precision, right? It will not give me the exact value. So once I have 18 here, I did the rounding here. So if I multiply or I divide 18 by 12.4509, this will not give me 1.5. This will give me something close to that, right? So there is a dequantization error. When you do quantization, you again do dequantization, there is a dequantization error, right? So this is how quantization works. You quantize, you save it, and when you actually have to work it, you have to dequantize it, right? So your memory requirements are limited because they become less because you are quantizing it to low precision. But when you are working, you are again taking it to a higher precision, and then you are doing all the multiplications and everything. Okay. So what were the major innovations that QLoRa brought in? So it brought in this 4-bit thing, and they had a specific data type. They are not using simply 4-bit where you will quantize them from so for 4-bit you will have minus 8 to 8, not like that, right? I mean, they had a minus 7 to 7, not like that. So they had a separate data type altogether. We'll talk about that. They did double quantization. We'll discuss what is that, and they used page optimization, right? So the 4-bit was the storage type, but they would compute always in bfloat16 data type, right? So they would do all computations on bfloat16, but they will store using 4-bit. Remember, all the weight matrices, we said only 4 bits are needed per weight, and that's where they saved. Okay. So what is this 4-bit normal float type? So idea is that typically these values that we are talking about, the weight matrices, they will be having some normal distribution, right? So when we say 4-bit, so I will have 16 buckets, right? So one way could be I can have some equally spaced buckets here, right, for the entire range, but that will not give me a good utilization. I would want each bucket should hold roughly equal number of values, right? Then only it makes sense. So each value should hold. So rather than having equally spaced buckets that I was talking about in terms of integers, why don't we have equally sized buckets? So each bucket should have equal size, even though the spacing is different, because as per distribution, a lot of values will lie here. So this bucket should be of smaller size. Then bucket here can be much larger because there are much less number of values here. So I can have a larger bucket, right? And this will help me in making a high precision quantization, right? Because if there are too many values, I want a very precise number, but if there are very little values, I can afford to lose on precision, right? So that's the idea. I will have equally sized bucket but not equally spaced buckets, right? Because most data sets are normally distributed and precision around mean is very important. So this is a nice thing about quantization. Now, how do I find these buckets, right? And this is not too difficult. So what they said, okay, let's assume a mean of 0 and standard deviation of 1 in normal distribution. Now you find equally spaced probabilities, like where will the probability, if you start from here, where will the probability will become, say this is probability is 0.5 up to here. Now you can go to the right, let's say I want to pick 8 values here in the positive side and 7 here in the negative side, right, and 1 will be 0. So I'll have 16 things. So how will I pick 8? So you equally divide the probability from 0 to 0.5. So you get these things 0.56, 0.62, 0.68. You see equal divisions in terms of probability, 0.73 and so on. And then you find what is the corresponding value for which you get the probability 0.56. So you get 0.15, 0.3 up to 1.85, right? So like that you get it. Now you put 0 also, and then you normalize it between -1 to 1. Yeah. So this is and this is the range that you get in this NF4 data type, right? And yeah, they are not, you see they are not equally sized. You have here they look roughly equal, 0.8, 0.8, 0.16, 0.25, 0.34, but you see this is increasing 0.44, 0.56, 0.72, 1, right? So that means because you will have more points here than here. So in this 0.7 to 1, you will have the same number of points as you will have between 0 to 0.08, right? So you will have each bucket should have theoretically, I mean, same number of elements. So you generate 8 evenly spaced values from here to here and 7 values from here to here, right? Calculate G values for the probability generated and divide by the absolute maximum value and you normalize. So this is how they create this NF4 data type, so that you don't lose on precision too much while using 4-bit, right? Rather than just using some equally spaced integers for storing this, right? So this was their data type. Now we talked about quantization, dequantization when you have equally sized things. In this case, how would you do quantization, dequantization? Let's take an example. So let's say again we have a tensor of any real data type x, and how would you apply quantization? So the first step will be same. So I'll find the absolute max of x and divide by that, so that x is in the range of -1 to 1. Now I have found these as my bins, right? These are the values in my bins, right? For after I divide each value by this x max, each value of x by x max, I'll find the nearest in this. What is the nearest integer here? And this one can use binary search or any other method, the nearest value. Okay, so let's take an example. So for 2-bit, right, 2-bit means 4 values. So we will have 0, 1, 2, 3, 4 indices. And let's say the value between -1 to 1 are these: -1, 0.3, 0.5, 1. So maybe in this distribution there were more elements on the positive side rather than negative side. So you have better quantization in the positive side than the negative side. Okay, let's say this is my input data point. So I have 4 values: 10, -3, 5, 4. I want to quantize and then dequantize back. So how do I quantize? First, what is the abs max? 10. So I normalize with that. So I get 1, -0.3, 0.5 and 0.4. This is the normalize with abs max. Now you find the closest values as per your quantization. So 1, the closest is 1. For -0.3, the closest seems to be 0.3, not -1. For 0.5, you have 0.5. For 0.4, you again have, you can take either of this. So let's say 0.5 here, right? And then you put back the index, and you only store these indices, right? Because these indices are what are 2 bits, right? So this indices can be stored in 2 bits. Now when you want to dequantize, so you will load this and then you look up. So you say, okay, index 3 was 1, and if I dequantize, I have to multiply with the constant 10. So I multiply 1 by 10. Similarly, 1 is 0.3, multiply by 10, I get 3. So I get 10355. You see, there is an error. I started with 10 minus 354 and I got 10355. There is a quantization error, right, in 2 bits. So, but yeah, this is how you can do when your values are fixed. These values are now these things. These things are your values in this case, right? You will use these values, and with 4 bits, that's how you will quantize and dequantize. So we have still not covered fully the Q-LoRa ingredients. We talked about only this data type that they use, but we'll talk more about that in the next lecture. Thank you.